Alright, let's get right down at it. I just want to review strong versus weak again, even though I know we've spoken about it already. Strong, acid or base, completely break apart. So if I dump HCl into water, I will get H+, which will in turn join up with a water molecule to give me H3O+, and I will get Cl-. I will have no HCl left after I dump it into a beaker of water. It will completely break apart. I will only have this and this. And the same thing with a strong base like NaOH. It will completely break apart into those ions. I will have no NaOH left. However, weak ones, only a small percentage would break apart. For example, acetic acid is a weak acid, and I think it's only about 3% here, and don't necessarily quote me on that, but I think it's only about 3% break up. So if I had 100 of these molecules, only 3 would break up to give me those things. The other 97 would just hang out just like they are, no problems. So strong acids are really easy to work with because whatever the concentration is here, let's say the concentration here is 2 moles per liter, I know that this would also be 2 moles per liter, and this would also be 2 moles per liter. Down here, I got to do some more complicated math, and we'll be talking about those in class or in later videos. Let's talk about the ion product constant of water. If I had a beaker of water, yes, and I got some water molecules, and believe it or not, they can actually react with each other to give me some H3O plus and some OH minus. In here, I would have H2Os. Vast majority would be just water molecules, but there's this very, very small amount would react with each other and give me a little bit of H3O plus and a little bit of OH minus. Now, if I was to write the KEQ for this reaction, it's products over reactants. Coefficients, 1 and 1, become exponents, 1 and 1, 2, 2. I'm going to swing this guy over. KEQ times H2O squared is equal to H3O plus. This guy lost a plus sign along the way. And OH minus. We have hopefully spoken about this concentration of water. It's the concentration of pure water. How much water is in water? C is N over V. If I do those calculations, I actually get it to be about 55.6 moles per liter, which is a huge number. Many, many moles in a liter of water. Many moles of water in a liter of water. And so in any sort of reaction, water, really, the concentration of water is not going to change. It might change a little bit. Used the analogy before. If you have $1 million and you buy a chocolate bar for $1, how much money do you have? You've still basically got $1 million, right? It's an approximation that we can feel confident making. So this value is pretty much not going to be changed over time. So it's constant. KEQ is constant. A constant times a constant is another constant. And in this case, because we're dealing with water, we use KW. Yeah. The ion product constant of water. Now, at 25 degrees Celsius, KW is 1 times 10 to the minus 14. Surprise face. Minus 14, isn't the pH scale, doesn't it go from like 1 to 14, or sorry, 0 to 14? Yeah, this is, that scale is a scale of 14 because of this value right here. Now, there's the formula again. H3O plus times OH minus is Kw. Kw is this. The amount of this in pure water and this would be the same, because every time I make one of these, I have to make one of those. So in this case, if I let this be x, and this be x, and this be 1 times 10 to the minus 14, to find x, I guess I would just x squared equals this, so x would be equal to the square root of 1 times 10 to the minus 14, so it means both here are going to be 1 times 10 to the minus 7 moles per liter. And so we do know that the concentration of H3O plus in a neutral solution of 7 we know that the concentration of H3O plus is in neutral is 7, and there's where the 7 is coming from. Now, although Kw is defined in terms of the dissociation of water, this equilibrium expression is valid for any aqueous solution. Okay. So, if I have a beaker, some solution, and I drop in some acid, yes, I will have some extra H3O plus in here. So I know that Kw is H3O plus, concentrated OH minus. So if this times this will always be 1 times 10 to the minus 14. Always. So if I had a beaker of water, they would both be, like I just wrote up here, 1 times 10 to the minus 7, 1 times 10 to the minus 7. If I dump in some acid, this value is going to get bigger. But this times this will always be 1 times 10 to the minus 14. So if I dump in acid, this gets bigger. Therefore, this must get smaller. Yes? So regardless of where this and this came from in a solution, this times this must always be 1 times 10 to the minus 14. So this equilibrium constant expression is equally valid for solutions of acids and bases dissolved in water. Regardless of the source of the H3O plus and OH minus ions in water, the product of these two concentrations at equilibrium at 25 degrees Celsius will always be 1 times 10 to the minus 14. So when one goes up, the other one has to go down. So keep that in mind.